All right, in this first video in chapter 14, we're going to introduce the idea of a double integral. And so let's first recall a few things about definite integrals for functions of a single variable. So let's say I have a function f of x defined over an interval ab, and I want to find the area bounded by this curve and the x-axis over this interval. And the complication here is that this boundary in general can be curved. And so the idea is to partition the interval into a bunch of smaller subintervals. And then over each subinterval, we're going to put one of these approximating rectangles. And then by adding up the areas of all those rectangles, we'll get an approximation to the area we're trying to find. And then observing that as we let the number of partitions increase, our approximations get better. That's going to lead us to a certain limit to find the exact value of this area. So what I just described there is what we call a Riemann sum approximation. And again, we partition the interval AB into n subintervals. We'll label those subdivision points x0, x1, x2, so on and so forth. And we'll assume that each subinterval has equal width. We'll call that width delta x, and it's equal to the length of the interval, which is just b minus a, divided by the number of subdivisions, which is n. And on each interval, we're going to choose what's called a sample point, labeled xi star, and this could be, say, a left endpoint or right endpoint, maybe a midpoint, and we're going to plug that into our function, and by doing so, that's going to give us the height of our approximating rectangle. And now if I multiply that height with the width delta x, that's going to give us the area of our approximating rectangle. And the sum of these rectangular areas, which I can write using sigma notation, is what's called a Riemann sum for our function f over the interval. And again, since the approximations get better and better as our number of subdivisions increases, we'll go ahead and define what's called the definite integral of our function f over the interval ab as the limit here as we let the number of subdivisions n approach infinity of these Riemann sums. Okay, now we'll say that the function f is integrable over the interval if this above limit exists for all possible choices of these sample points, and those limits all have a common value. Okay, and now a few comments before we move on to double integrals. One is that, again, just to reiterate, this definite integral here is computing for us the exact value of this area bounded by our curve in the x-axis over this interval. And as far as the notation is concerned, you want to read the f of x as telling us the height of a differential rectangle whose width is this, well, differential width dx. Okay, and this integral symbol is telling you, hey, add up all these differential areas as we let x range from a to b, and that's going to give you the overall area. Okay, so now let's go ahead and turn to a function of two variables, right? So we're now looking at a surface, and I'll assume that the function's defined over a rectangle, and I'll call that R. And so now we're asking, well, how do I find the volume bounded by our surface in the xy plane over this rectangle R? Okay, so here's a view of the xy plane in our rectangle. And now what we're going to do is partition this region here in red into a bunch of smaller subrectangles. Okay, and you can see I'm partitioning the interval AB as well as CD in much the same way we did for the Calc 1 or Calc 2 integral. And at least in principle, the number of subdivisions for the two intervals does not have to be the same. So that's why you see an N here and an M here. Okay, and now for the area of each one of these little sub-rectangles, okay, I'm going to call that delta A, and that's just going to be the product of these widths delta X and delta Y there, right? So now back in the 3D picture, what are we going to do? Well, over each one of these little sub-rectangles, we're going to form one of these approximating pillars, okay, and to find the height of one of these pillars, we're just going to choose a point in our subrectangle, and I'll call that point xi star yj star. And notice now we have two indices to contend with, right? Because we're really now having to range over both rows and columns. So we're going to plug that chosen point into our function, and that's going to tell us the height of our pillar. And then we're going to multiply that by the area of the base, which is just delta A, and that's going to give us the volume of this approximating pillar. And then, of course, we're just going to add up the volumes of all these approximating pillars. That'll give us an approximation of the volume. And then, since the approximations will get better and better as we let the number of subdivisions grow, this will lead us to the following definition, okay? So we'll suppose that our function f is nice and continuous, which will always be an assumption for us. And our rectangle here, r, is, I'll say more about this notation in the examples to come, but this is just saying x ranges from a to b and y ranges from c to d. And we'll define the double integral of our function f over this rectangle, which is written now with two integral symbols. And this little subscript r is just indicating the region we're integrating over, is defined by this limit, right? This almost sort of double limit looking thing, right? And really the idea, as horrendous as this might look, the idea is exactly the same as what we did back in Calc 1, Calc 2, okay? So this thing here, underlined in orange, again, is just the volume of one of these pillars. And this double sum here is just summing us over the rows and the columns of our grid, and it's in turn going to give us a Riemann sum approximation to the entire volume, right, bounded by our surface in the xy plane over this rectangle, okay? Then the limit there is just going to pass us from an approximation to the exact value of the volume, which is what the double integral here represents, okay? And again, a note here on notation, f is the height of the pillar, and then we're multiplying that with the differential area dA, that's the area of the base of this little differential rectangle, and that product is a volume of one of these little pillars. And then these integral symbols here are saying, okay, now add those the volumes up as you let your points range over this region R, and you're going to get the overall volume. Okay, so on that note, my next comment here is on just interpreting a double integral in terms of volumes, right? So if your function's non-negative, just like in the last slide, right, this double integral is just going to tell you that volume under your graph and above this rectangle, right? Just like you see in this figure here. But as you know from Calc 2, right, if your function takes on both, say, positive and negative values, right, then the integral is really giving you a signed area, right? And we're going to take that same interpretation when it comes to a double integral, right? So if our function takes on both positive and negative values of our r, so let's say there's a portion of our surface that lives above the xy plane and a portion that lives below, then this double integral here is going to tell us the signed volume bounded by the graph of f and our rectangle r. Okay, so let's say, you know, this volume in green was 7, and this volume in purple there is, say, -5. This double integral would compute that as 7 minus 5 would be 2, right? It's giving you sort of the net signed volume, so to speak. Okay, cool. So now, as you might suspect, we are likely not going to use that limit definition to actually compute these double integrals, right? That would be a horrendous mess. Okay, so much like we saw with partial derivatives, where we define those in terms of difference quotients, we then took a slightly different perspective and arrived at a computational method that allowed us to fall back on stuff we know from Calc 1 and 2. We'll do the same thing here. Okay, so the key is that instead of looking at a bunch of pillars and letting those pillar volumes sort of range over the region R, instead what we can do is think about cross sections. So let's say, for example, I fix Y. Then I can consider this cross section, right, that's cut out here by this plane at Y, and I can compute this cross-sectional area here by just thinking, well, look, this is just really a Calc 2 kind of an area, right? The profile curve up here is just the cross-section of our surface. So in other words, it's just, the height there is just our function f. And again, keep in mind that y here is being held constant. And now I'm going to integrate that as we let x range from, well, a to b. So you see x here ranges from a to b in this integral. And this cross-sectional area will depend on the choice for y, right? So if I choose y to be a point in this interval CD, okay, as you move through C to D, right, this cross-sectional area can change. So that's why I'm saying a of y is equal to this integral here. All right, so if that's just the cross-sectional area, then how do I go from that to the volume? Well, the idea now is like stacking a bunch of slabs, right? We're now going to let these slabs add up as we let y range from C to D. So in other words, I'm going to integrate this cross-sectional area function with respect to y as we let y go from C to D. So stacking those slabs, we're going to arrive at the total volume, okay? And now the thing to notice here is that this area itself, the a of y, is just this integral right here. So if you replace a of y with that integral, you arrive at this thing, which is what we're going to call an iterated integral. Okay, so we're going to integrate with respect to x first, holding y constant, and then we're going to integrate the resulting expression with respect to y. Okay. All right, so the next thing I want to say is that, well, there's nothing special about, fixing y first and then letting x vary. We just as well could say fix x and then let y vary. Okay, so in other words, compute these cross-sectional areas, and I'll call those a of x, so much the same way. Okay, this now, we're looking at this profile curve as we let y range from C to D. Okay, so that integral right here, we just compute that cross-sectional area. And then to find the volume, we're just going to go ahead and stack these slabs as we let x range from A to B. So I'm going to integrate this cross-sectional area, and that's going to lead to this iterated integral. Okay, and there's a big theorem here in this section called Fubini's theorem, and I just make a little comment here. This thing only applies to rectangles. Okay, we'll look at more general regions shortly, where we're going to have to be a little more careful. But what it says is that, look, the double integral, which if your function is non-negative, is really just telling you the volume of this region, can be computed either in that first cross-sectional approach, right, again, where we had that vision, or we can do it with this other cross-sectional approach, right? The two approaches will just give you that same volume there, right? So in other words, these iterated integrals over our rectangle are equal. All right, so we're going to stop there. In the next video, we're going to look at how to go about computing these iterated integrals, and I will see you there. Thanks.